In this video, we're going to review the properties of logarithms, which are going to help us to rewrite complex functions so that they're easier to do derivatives and antiderivatives. So here we go. Logarithms and exponentials are inverse functions. So if I write something in exponential form, b to the y is equal to x, I can convert that to logarithmic form. And that would be the log with a base of b of x is equal to y. So a logarithm allows you to isolate the exponent y. There's a special number that deals with logarithms called e. So if I have log base e of x equal to y, well, that's the same thing as saying the natural log of x is equal to y. This is the one and only time you don't need to write a base, and therefore there's a different notation, ln of x, instead of log base b of x. So how do you go through and rewrite exponential expressions in terms of logarithmic form? Now, we're not going to go through and solve for x or y in these problems. We're just going to rewrite them in logarithmic form, like what's written in blue up top. So the first one, 2 to the x is equal to 8. So the base is 2, and the exponent is x, and what it's equal to is the 8. So we're going to write log, then write the base. What it's equal to comes next, and the exponent gets isolated on its own. So log base 2 of 8 is equal to x. The next one, the base is 5, the exponent is 6y. So we're going to have log base 5, the exponent gets shifted off by itself. That's what it's going to be equal to. So the 125 goes inside of the logarithm. So it's log base 5 of 125 is equal to 6y. And then for the last one, the base here is 9. So this is log base 9 of what it's equal to, 1/9, is equal to the exponent x. All right? So that's just converting from exponential form to logarithmic form. You should be comfortable going between these two forms. The properties of logarithms. Now these are all things that you have seen before. Log base b of 1 is equal to a special number. If we take a look at that, that would be b to some exponent is equal to 1. What would the exponent be? The exponent would have to be 0, because b to the 0 power is equal to 1. So log base b of 1 is 0. And the b means any numerical base, which is any positive number. All right, log base b of b. That means b to the something is equal to b. What would go in the box? Well, that would have to be an exponent of 1. So if the base and the thing inside the logarithm are the same, then that is equal to 1. Right? Log base b of b to the x. That means b to the something is equal to b to the x. So that means that the box is filled with an x. So log base b of b to the x is equal to x. So if the base here and the base here are the same, the answer is just the exponent. b to a logarithm. If the two bases are the same, this ends up being equal to the inside portion right here. This is also equal to x. We're not going to go through why that is. We're just going to accept it. You can ask me why in class if you would like. And then log base b of x to the n. What we can do here is we can take the exponent and pull it out in front. So this is really n log base b of x. So exponents can be pulled out in front. Number 6 is a spin-off of number 5. For starters, this is log base b of x to the negative 1. And then I can bring the exponent out in front. So it'll be negative log base b of x. So that'll happen whenever you have a fraction on the inside. You can put a negative out in front and then do the reciprocal on the inside. Right, there are two more properties. These can be used to expand an expression. Right, log base b of xy. When there's a product inside, that turns into a summation. So log base b of x plus log base b of y. Similarly, if there's a quotient inside, it becomes a difference. Log base b of x minus log base b of y. So we can use these properties to expand different problems. So when I look at problem number 1, I see the base is 3, and inside I have a quotient. So for starters, I'm going to say this is log base 3 of the numerator, 3x, minus log base 3 of the denominator, y. Okay. Next, the 3x is technically a product. It is 3 times x. So I'm going to say this is log base 3 of 3 plus log base 3 of x. And then I still have minus log base 3 of y. And there's one more thing I can do here. What is log base 3 of 3? Well, if the base and the number are the same, then that is equal to 1. And this is fully expanded. So it's 1 minus log base 3 of x. I'm sorry, plus log base 3 of x minus log base 3 of y. All right, 2 more expansion problems. Let's expand the natural log. Remember, this is the same rules as a regular log. We're just writing ln instead of log in a base. For starters, there's a product right here. 4 times this. So this is ln of 4 plus ln of x plus 2y quantity cubed. Next, that second natural log has an exponent, so I can pull that exponent out in front. So we have ln of 4 plus 3 ln of x plus 2y. That is as far as this can be expanded. The x plus 2y is a sum, not a product, not a quotient, so I can't split it apart at all. So this is our final answer. For the last one, we have a radical and a quotient. So I'm going to start by rewriting this as ln of x plus y divided by z all to the 1/2 power. And then I can bring that 1/2 exponent out in front. So that would be 1/2 ln of x plus y divided by z. And then inside the parentheses I have a quotient, so I can split it again. So this is 1/2 ln of the top minus, I have to distribute the 1/2 here, 1/2 ln of z. And the x plus y, since it's a sum, I cannot split it any further. So this is fully expanded. Similar to expanding, we can condense an expression and take something that is lengthy and condense it down into a single logarithm. So let's take a look at how to do that. So on this first problem, I'm going to start by dealing with this 1/2 in front. And keep in mind that 1/2 only applies to the first logarithm. So here, we are going to make this an exponent, log base 6 of 144 to the 1/2. And then it's minus log base 6 of 2. All right. What is 144 to the 1/2 power? Well, that's the same thing as the square root of 144. So this is really log base 6 of 12 minus log base 6 of 2. Since there's subtraction between the two logarithms, that means I originally had a quotient. So this is now going to become log base 6 of 12 over 2, which we know 12 over 2 is really just 6, log base 6 of 6. And since the base and the number inside are equal, this answer is 1. So 1/2 log base 6 of 144 minus log base 6 of 2 is a very complicated way of writing the number 1. All right, this second one's still going to have variables involved, so it will not be a single numerical value. For starters, all of the coefficients out in front can be brought back in as exponents. So I'm going to start with that. So I'm going to have log base 3 of x squared plus log base 3 of y to the 5th minus log base 3 of z to the 7th. Now I could make that a negative 7 exponent and change this to addition, but I'm going to keep it as subtraction to try to make it a little bit easier on myself. Let's try to avoid negative exponents. All right, next I have a sum right here, which means I can make x squared and y to the 5th become a product. So this is now equal to log base 3 of x squared y to the 5th minus log base 3 of z to the 7th. And now, because I have the subtraction here, I can make this into a quotient, and then we'll be done. This is log base 3 of x squared y to the 5th, all divided by z to the 7th. And that's the final condensed version. All right, one more like this. We are going to condense 5 plus ln 4 minus 2 ln k. All right, for starters, 5 is a single number. It doesn't have an ln in it. So we need to get an ln in there. So how are we going to do that? Well, would you believe me if I told you that this is the ln of e to the 5th? Here's why. This is technically log base e of e to the 5th. And since the base is the same as the base in the e to the 5th, e and e, it's equal to the exponent 5. We'll talk more about how to deal with condensing with a single number in class tomorrow. All right, now we have plus the ln of 4 minus, this can go up top and become an exponent, ln of k squared. Then we have a sum at the beginning, so I can make this the ln of e to the 5th times 4, or 4e to the 5th, minus the ln of k squared. And then I have a difference, which makes a quotient. This is the ln of 4e to the 5th, all over k squared. Okay. So that's condensing. It's more important that you know how to expand at this point than it is that you know how to condense. But both skills are important to know. All right, so what is the point of having logarithms? Why do we need them? And the answer for that is fairly simple. We need logarithms to solve exponential equations. So we're going to take a look at two exponential equations to solve. One we can technically solve without a logarithm very quickly. The other one requires logarithms. Let's see why. All right, we're going to solve 2 to the x is equal to 16. Well, this one should be pretty easy for you guys. 2 to what power is equal to 16? If you think about it, you should come up with x is equal to 4. But how could we use logarithms to figure that out? Well, if I rewrite this in logarithmic form, it would be log, the base is 2, of the answer 16 is equal to x. Well, 16 can be written as 2 to the 4th power, and then since the bases are the same, the answer is just the exponent, which is 4. Right. So yes, looking at the first one, it's much easier to just look at it and reason your way to an answer. But problem number 2, 4 to the x is equal to 7, there's no way for me to try to figure out what the exponent would be so that when I raise 4 to that exponent I get 7, because 4 and 7 don't have any common factors at all. So in order to do this, I would have to use a logarithm. So this would be log base 4 of 7 is equal to x. There was a formula called change of base formula in order to solve something like this on a calculator. In order to do it, we would do the logarithm of the tall number, 7, divided by the logarithm of the base. And when we write just plain old log like this, that is log base 10, or common log, which is programmed into your calculator. Okay? So then if we typed in log of 7 divided by log of 4 on the calculator, we would get that x is approximately equal to 1.404. Good luck figuring that out without a calculator. All right. The last thing is finding an exact value without using a calculator. So this again just comes down to, can you rewrite it either as an exponential equation and reason your way to an answer, or use properties of logs? So I'm going to take a look at this first one. What's another way to write 125? And we want it to be in terms of the 5 that is the base. So 125 is equal to 5 to the third. So this could be log base 5 of 5 to the third. And since the bases are the same, the answer is just the exponent 3. The other way you could think of it is if we treated it as log base 5 of 125 is equal to x, we would have 5 to the x is equal to 125. And then you should be able to figure out that 5 to the third power, x equals 3. So the numerical value would be 3. All right, and then for our last problem of this video, log base 4 of 32. Well, this one would be harder because I can't write 32 as 4 to an exponent, or at least not right away. So we're actually going to say, okay, pretend this is equal to x, now convert it to an exponential equation. That means 4 to the x power is equal to 32. Now that doesn't seem to make it much easier, but if I think about it, 4 can be written as 2 squared. So this is 2 squared to the x power. And I can write 32 as 2 to the 5th power. When I have an exponent times an exponent, or an exponent to an exponent rather, I multiply them. So this is 2 to the 2x is equal to 2 to the 5th. That means 2x is equal to 5, x equals 5 over 2. Okay? So this expression is equal to 5/2. Again, it's probably easier to look at that in terms of an exponential equation than it is to work with it as a logarithm. All right. I hope that this was clear. We'll go over any questions in class tomorrow.